see next to me. So you already have seen a PSM before, so I'm not going to show you the PSM.
Okay.
But here, this is the latest version, as far as I know, of the PSM alignment software running live. As you can see, we are live. If I put my hand hereby. And here, you have the Zernike module or the AI wavefront sensing capability, which is enabled. That's a feature our customer buy on top of the PSM. Make a long story short, when you buy it, you get a key. But basically, you get a file which is encrypted for your machine. You can download, and when you download that, this open the feature in the software.
So,
And yeah,
but this is a software key,
yeah,
not a hardware key.
That's right. So the way it works is the customer, I'll show you that quick. On the Zernike, if you go here, you see, well, it's probably on settings, Zernike module. You can get the machine ID where you are running the software. If I click it, I get a number, right? And when you give me this machine ID, I create a file for your PSM. Then you can load the file. The file is encrypted based to this machine ID. Basically, the machine ID is a public key. And the file is encrypted with that, and it will work only on that machine. So when the system recognizes the file and is able to define, use the private key to access the file, then all the options for Zernike, the coefficient, everything will appear. Otherwise, the PSM will work just like usually for alignment. And you can always actually, if you want, anytime you can come here and say, in general, I think he's here. I don't want the PSM doing any wavefront measurement. I want just a standard PSM alignment. If I say OK here, you will see the PSM now is providing only information here about the typical measurements. It was so small, but well, in settings, that's where I went before under Zernike stuff to get the machine ID I was talking about. And this cryptic number is a public key used to encrypt this file anyway.
Okay.
So let's go.
I remember that.
Let's go back here and have the Zernike module enabled, right? And so now, normally, of course, when you do alignment, you are in focus with the PSM. But here, the whole idea is to defocus. And here, when you activate the Zernike module for the PSM, it will automatically show you a blue circle, which is the size of the expected size of the defocus image you should aim for.
Okay.
You understand? So if I move here, you will see this is a defocus image.
Yes.
And I'm actually measuring a spherical mirror. So I'm at the center of curvature of the mirror with the microscope objective of the PSM here in this setup.
Yes.
So it's a concave, a small mirror I use on my bench. You have seen the bench before, but it could be anything, right? It could be whatever. So this is a defocus image of it. And you can change the defocus here by moving the mirror back and forth.
Right.
So your goal is to come close to this diameter. You don't need to be perfect. You just need to come close enough. And so when you do that and you are ready, you can click to the calculate button here.
But wait.
Yeah.
Do you have to inform the software in which direction you defocus?
Yes, that's right. Okay. And so these are, it's a very good question. Those are parameters under Zernike. Where is it? I think it's here, Zernike parameters. As you can see, I'm not sure if you can read well, but those are the key parameters the user is going to enter.
Okay.
There are some threshold for automatic detection, but beside this, you have to provide the PSM aperture, which is set at 5 millimeter here, which is inside the PSM. The focal length of the PSM is 100, is always the same. but you can change it if you have something else.
Mhm.
The focal length of the objective in use, the pixel size of the camera in use at the PSM. The PSM may come with different cameras.
Mhm.
The wavelengths, today we are running with the internal laser of the PSM, but you could use an external laser.
Mhm.
The beam waste, which has to do with the beam apodization from the
Mhm.
PSM, which is typically 1.5. And there is also a number named here, fill factor, who define this number is 1 if you underfill the target, meaning if the PSM is a system stop. Now, if you overfill the target, meaning your mirror, for instance, or your optics become the system stop, who stop the beam, then this factor will be below 1 to tell the system not all the beams come back. You see what I mean? Because you could have a beam from the PSM in this example, it's spherical wave, which is larger than the part you are measuring. So that's where you tell the system only 50% of the beam comes back in terms of diameter, right?
So wait a minute. What I think I understand is that you're underfilling your sensor.
The target, the mirror here, I'm underfilling the mirror. I'm not measuring the whole surface of the mirror in this case. But if I fill the whole surface of the mirror, the fill factor will still be 1 because what's defined, the system stop is still the PSM who define the beam. But if the beam is stopped by the target, like the mirror is smaller than the beam at the mirror location,
Ah,
then the mirror becomes a stop. And that's where you have to adjust this factor to tell the system it needs to know there is another stop in the system than the 5 millimeter here you have below. It's coming from the fact you are overfilling the part you are measuring.
right.
That's just technical detail, but those parameters are entered by the customer when he wants to use the system. It's all he needs to enter. And when he's entered, those parameters will define the size of this circle here automatically, right?
But Fred was asking about the
Let me use this.
the focus,
Yeah. So
extra focus.
why? Just give me a
I
second.
didn't see it on those
Yeah,
parameters.
yeah. I have two mouse, so I need to move this one away. Give me 1 second because the PSM is, I have a second mouse with a PSM, but probably you don't see the second mouse, right? You only
Right.
see that. So, okay. So yeah, let's go back here because you can see this one, right? You see my mouse, you see my cursor.
Right.
Sorry.
Yes.
Yeah. So, if for any reason you are by default, it's an extrafocal defocus. Now, if you go intrafocal, you will just click here and say, I want to flip the Zernike coefficients because he will do automatically the flipping to account for the fact you are on the other side of the focus.
Well, you say the other side. Um,
Intra, because the model is designed for extra by default.
so intra relative, what does that mean? Which direction?
Okay, let me define it. Focus is focus, right? Intrafocal is when you are moving in that case, the PSM toward the target, closer to the target. Extrafocal, you are moving away from the focal plane.
Mm.
In that case, from the center of curvature. We are actually next to the center of curvature of the spherical mirror. So if I move the PSM at the center of curvature, I will get a focus point, right? Because it's a
Right.
spherical mirror and a
Right.
spherical wave. If I move away from the mirror, that's my definition of extrafocal. I'm moving away from the center
Okay.
of curvature,
Okay.
away from the mirror. And that's done by moving the PSM, in fact, just a little bit.
Or the
So,
optic.
or the optics. In that case, I'm moving the mirror away from the PSM, which make me imaging back the return after the focus.
Right.
So by default, this is a configuration we expect. If you change the configuration and for any reason you need to focus, need to be out of focus before the CC, then you have just to tell the system by saying you need to flip my Zernike coefficients because they actually flip. You follow me?
I do.
So those are the parameters the user will enter. And now, yeah.
I'm sorry.
Yeah.
In my experience, the typical operator has no idea how to measure the beam waste or know the beam waste
No, he
of.
doesn't need to know. We can tell him that.
Okay.
Yeah, it's a value the user usually doesn't change.
Yeah.
He may be related to a given PSM, but it's not a value we expect him to change at that stage.
Okay.
Only the other values we were talking about are something the user would probably change. Although the internal values for the PSM, like the 100 millimeter focal length of the tube length, there is no reason he will ever change it, because this is an internal setup of the PSM itself. But it's there because what we use behind the scene, the library or does all the calculation, can be used for any other system. If you would have an autocollimator, to pick an example, then those values may be different.
Yes.
And we already have the capability to do so. But for the PSM, they are pretty much always the same. So now what you see, if I move
I'm sorry. One more.
Yeah.
So with the PSM, if you change the objective,
Yeah.
that comes into play as well, right?
Yes. And if you do that, you want to change the value here. Under parameter, you see the objective focal length.
Okay.
It doesn't have an impact to the calculation of the wavefront, but it does have an impact to the size of the circle you see there for the defocus for the user, because it changed the scale at the object at the image of the image, right? And so for the user to have the right diameter for the circle, you need to provide the right magnification of the objective. It's also used at few other locations for the display. So now I did what I could, hopefully, to defocus extra focal in that case, moving the PSM like way less than a millimeter here away from the CC. And I get this slightly defocus image. And if I click under calculate below here, few seconds later, you see he's doing running, and then you get those values. And you will see more than that soon, but I show you the values first. So the first value on the top in green, and you want to be green, it's the residual error between the expected defocus and the actual defocus in microns. And that's where the value of the objective focal length is important, because this value is calibrated relative to the magnification of the system. So what the system says here, based on the wavefront analysis, in that case the defocus, it tells you, well, I've done a good job. I'm only -6 microns short of the expected defocus position. So if I have a scale, I could just adjust by 6 microns, moving a little bit more the mirror or the PSM, and that will bring me to 0. It's a measurement how far you are from the expected defocus. The defocus design when we build a model. Now, the model has a range of tolerance on the defocus. So it's why you don't need perfectly accurate. Okay. And as long as it's green, it tells you you are not perfect, but you're good enough. You are in green range. Okay? So I'll show you what's happened if, let's finish with the number. Below it, you have the actual defocus error in wave RMS, which has been used to compute the radial distance, right? The axial distance, the -6 microns here, because we have -0.02 wave of defocus. We are not exactly where the defocus error here is the difference between where you're supposed to be and where you are in terms of wave defocus.
Then also green?
Yeah. Well, no, the color is only for the conversion in microns, because that's probably where people are more interested, is how much I need to move to be at the right place. But those two numbers are fully related to each other.
So the question is, if you're trying to get maximum precision,
You want to be
let's
green.
say you're at lambda over 20 and you have this defocusing error that's still green. Let's say if you set it to 0, will the operator see a difference in the peak to valley RMS or sub what?
Yeah, you may see some variation, but we are talking about thousands of a wave.
Thousands of waves. Okay,
Yeah, yeah.
that's my question.
So
Okay,
it's very little. So it's
okay,
why if you stay on the green range, you should be good
okay.
to a few thousand of a wave. And let me show you that. But before I should, well, after that, you have the Zernike coefficients, right? Now, all in wave RMS. And I'll show you more than that later. And by the way, by default, those coefficients, if you ask for, they are saved in a result file, which is an Excel file. So you can open them under Excel
Ah,
and see for every data you took, and I'll show you that later, what the results were, right?
okay.
So
So I'm sorry to
yeah,
interrupt again.
go
So
ahead.
let's say this is part 1, 2, 3 in a production cycle.
Yeah,
Can you name it and
yes,
save this as a recipe?
yes. I'll show you that a bit later. Let me finish with
Okay,
the PSM Align software, and then we'll talk about the viewer who
okay,
does all of that for you. But the way both work together is the PSM software is a standalone software. It will create this Excel file and put the data as they come, right?
okay,
The viewer, you will see later, is going to look at that file, and every time there's a new data point, he's going to take it and show you the results. And you can create a report and everything with that. But they work independently as we speak. Uh, Let me do one test here. I'm going to change a little bit the defocus and let's say defocus a bit less, right? Moving my mirror closer to the PSM.
right.
So I'm a little bit inside the blue circle. See what he says. And you see now I'm minus 30 microns. I'm in orange color, which tells me I'm outside my expected
Ah,
tolerance range.
right.
So I should probably correct, and is what I'm going to do. And of course, if you can go to 0, it's even great, but you don't need to be at 0. That's the whole
Yeah.
idea. So you see how good I am now. It looks like I'm always at minus 6. Well, anyway, so this is what you get from the PSM software, which save the data. You have also the capability to take the data here and use save them on an Excel, which is used for calibration, which means eventually we can remove those coefficients from a calibrated situation from any new data. So now let me show you the viewer. The viewer is a piece of code which use the data from the Zernike, from the PSM, from the Excel file. So this viewer is very basic. It's an application running independently of the PSM.
Mhm.
It's just monitoring a file named PSM Excel file where you have to tell where the file is, right?
Ah, right.
It turns out my file now is named data result, which is the same which has been defined in the PSM software.
Right.
But it could be any file, but this in that case I want transfer of the result right there. And you also the system will automatically find, but you can always tell him where is the PSM setting file, because the PSM's all the setting of the PSM which you may use on this calculation are in a PSM setting file named TOML in app data blah blah blah.
Okay.
So the software knows that we have an agreement with the Gary who wrote the PSM where to put the configuration file for the PSM.
Mhm.
But you can always go manually if you want to actually. It will automatically find it and put the right path here. The next one I'll show you later. It's an interesting feature if you don't have a circular aperture. And we have an example of that. After that, you can set up some information about swapping X, Y axis of the camera depending on the orientation of the PSM. X, Y axis flips depending if you have a reflection in between, those kind of classical problem. Here you see he says from the PSM data, he says, I'm extrafocal. I'm not intrafocal. He says false. I'm in double pass, which is a default also. You can also be in single pass, but with the standard PSM, you're in double pass. And then those data are coming from the PSM parameters we just saw before. The defocus bias is the value for the mathematical model in use by the PSM. The wavelength is 640 by default. The fill factor, we know it's 1. But if I change it on the PSM, it will change here. The spot, the aperture stop was 5 millimeter. And this is even the name of the file in use for the mathematical model.
Mm-hmm.
And you see the line after that says, by default, any new entry on the Excel file will be automatically processed by the system. And on the bottom here, you have the list of all, probably better if I use this mouse, but you don't see the cursor. Here, sorry. Here you see it's an Excel table, basically, with all the measurement I took on the file. And if you look carefully, the last one was just now.
So for the operator who has a new part, is this going to be part of the expected setup for a new lens or optical system?
Yeah, the idea is if you have something you want to measure, you just create an Excel file with the name you like. That's my recommendation. You use this Excel file in a PSM, and you set the same Excel file on the viewer. And my suggestion is to use an Excel file every time a new one, maybe related to the part number and everything like that, such you know all your measurements here come from the same thing. Because here I have a lot of them. I have 321 measurements just because I did a lot of tests. But every time you take a measurement, you get the date and the time of it. All the coefficients of the Zernike found by the system. And you can even simulate values here if you want to try. And if you look carefully here, I'll skip for now, the mask is just a standard circular mask. From this, you get the Zernike.
I'm sorry to interrupt. Can you put in a % of clear aperture mask?
Not yet, but we could, yes.
Okay, that's
right. Now it's 100. Well, now I think it's 98 by default. But I'm thinking to add a value here where you can define the size of the maximum in % of the diameter, like 95, 90, or 98.
Excellent. Okay.
Now, you can rotate the mask, but it's not going to help you here because it's a circular mask anyway. But I'll show you another mask later. Now, so either you select a line here, the line in blue is the selected line. So I can pick any of those if I want to compare a result from before. But by default, it will select the last one, which the last one who was updated in the system. So here you see the Zernike from that line. And those values should be identical to the PSM. So if we look at, for instance, the defocus error, it was minus 0.22. You see here, minus 0.22. So those are the values we got from the PSM, displayed in a bar chart. And you can decide to deselect some if you want to see how does it look when they are not there. It shows you the coefficient were taken right now. This PC has 1 hour behind us. I don't know why. But the total RMS error for this data, the PV. But if you want to know more, you go to wavefront. And on wavefront, you get, after removing tilt and power, you get the 2D heat plot with cross-section XY for now, in wave and in nanometer. And if you want, you can also go as automatic scale, but you can have a custom scale and say, I want to put my scale between blah and blah, blah, and blah, blah. And in that case, and change my unit from wave to nanometer on a color plot. And so you have the option to say, I want a custom scale. By default, is using these two values, which are automatic, but I can change that. No, I'll stay automatic for now, but
Ah,
I
okay.
can say I don't want wave, I want nanometer on the right here. Let's go for the people who are missing the fringes. You can get them here. And one thing I didn't mention is the data we got from the PSM has been calibrated. So the PSM aberration has been removed. So what we see is only the mirror. And this mirror is not too bad. As you can see,
Right.
we have about 0.04 wave PV,
Right.
right? Which is not bad on this mirror.
Yeah.
Is is better than over 20. So the flange looks pretty straight because the mirror is good.
Right.
From there, you have the MTF,
So
and
I'm sorry to go back
no,
to
go ahead.
2D.
Yeah,
Red means high.
yeah, you have the scale on the right.
I know it's a scale on the right.
Positive is high peaks, and blue are troughs.
Okay.
So it seems we have a little bit some maybe spherical aberration. If you look at the Zernike coefficients, the dominant error, beside the defocus, but the defocus is not shown on the wavefront, right? We only show the other one, and the dominant one is a little bit some comma,
Yeah.
astigmatism, a comma, 1,000 of a wave, right? And a little bit some spherical, not much.
Yeah.
So, but it's an auto scale, huh? So it's why you see something. If I would say I don't want to set my scale, I may not see all of that. If I go here and I say I want to set my scale in, let's say, nanometer between uh, minus 50 to minus plus 50, well, it looks pretty flat. You see what I mean?
So if you don't fool with that, does the system automatically set its boundaries?
Yes, that's
No.
exactly what's happened when you click on automatic here.
Okay. Okay.
And so what you see now is going to scale automatically the max and mean for you
Mhm.
for the color plot and for the cross sections.
Mhm.
On cross section, you can see both the waves and the nanometer always.
Yeah, I mean the only
Well, one thing you have if you hover the cursor at the location, you see you don't see it because it's too small for you. But on the top right, you see the position and the magnitude of the error.
right.
So if I go on the blue, it will be negative minus
Oh, cool.
0.2. If you go here, you are positive 0.010. And you can zoom in if you like, see better what's going on here.
Okay. I mean, that would
But
be
those,
good if you had roughness or asperities or defects. Yeah.
now, the fringes, I think we talk about it, but it's only for convenience, for the people who like to see them. MTF, it's obvious. You see the actual MTF and the theoretical MTF, but you don't see
Perfect.
any difference. Also, I show you later. And the reconstructed image, just to get a feeling of what you're supposed to see. So now, let me do one. And now we forget this one. It's important. You can create a report. And you can put a title to the report, my report. The company, my company,
Sure.
me, right?
Operator.
Today, whatever you like. Part number 1, 2, 3, 4, 5, 6.
Oh, sure.
Radius of curvature. If you use the PSM to measure the radius of curvature, you can record this one here. Say it was 806.3 millimeter. You can add a comment as much as you like, right?
Right.
You can have eventually none or pass or failed. Let's say we'll say pass here. Mark. And you
So
can
wait. Can you set pass-fail parameters?
no, only globally at that stage. Is you decide if he passed or not.
Okay.
But you can put comments here and say, I failed because,
Yeah,
if you
yeah.
like. It's a totally free text.
So,
Uh,
so this worksheet is only for curved optics.
uh, well, if you use the PSM like now, yes. But it could be used on a concave, convex too.
But
Um,
say you can use the PSM to look at flat optics.
to do that, you have to remove the objective.
Right.
And you can use the PSM to measure also a convex one, as long as you have enough working distance with the PSM macroscope objective. After that, you need to put an optic to address the problem of convex surface with the PSM. It has nothing to do with our technology, though. It has to do with the way the PSM optics works.
Sure. But I mean, I'm hoping that they're at the outset, when the operator turns it on, it's going to say, do you want to look at a flat, a recipe, or a curve?
Yes,
Okay.
but for now, again, that's an early stage and it's tailored for the PSM.
Okay.
Having said all of that, if we talk later about using that in an autocollimator or another setup, we can easily change this to adapt to other things.
Sure.
Now, the preview show you how the report will looks like. So it will be my information. Here I said I passed. I have my comment, which doesn't make much sense in this case.
Mm-hmm.
The PSM parameter used for the measurements. Um, and you see the results we saw before
Mm-hmm.
in a report. And you can come here and say, I want to save this report as a PDF. And you get a PDF version of the report. You can do whatever you like with that.
Yeah, yeah.
Now, if I go back here, let's go Zernike for now. I'm going to do something interesting. I'm going to warp the mirror. So let's turn the screw. Here we are. See, my mirror now is a bit warped.
Yep.
So I would just recenter the stuff in the middle here, more or less.
By the way, let me interrupt you with reporting.
Yeah.
Is there a way to look or to save this screen as the report? Because that's probably the most likely use for it.
Yes, you can. Actually, for every screen, it's a good question. For every screen, you have the option to click on this floppy disk,
Okay.
and you will do a PNG version of it.
Okay.
And you can save the figure. So you
Perfect.
can save the report, you can save whatever. The report is automatically, if you ask for, you can save it as a PDF. Oh, let me show you what's happened now. I did stress a bit the mirror. As you can see, I have something like astigmatism. So if I do calculate, it's doing calculation. I'm minus 14. I'm still green, so it's not bad.
Mm-hmm.
Look here now on the settings. I get 322, which is just now automatically selected. And if I look at the Zernike, oops, I have oblique astigmatism. You would expect because I just my
Mm-hmm.
screw is at 45 degrees. So now you can start to see the effect
Yeah, yeah, yeah.
on a plot. Now you have some things to see on the fringes, finally, and on the MTF. And the
Yes.
MTF expected is red, but yours is not good. And the reconstruction show you the elongated shape we have on the PSM
Mm-hmm.
image, which is basically this one, right? Except there is no noise, nothing like that. It's
Right.
almost perfect. So now I hate when I see something so bad. Let me release the pressure on the mirror because what I wanted to show you, since it's already part, we have a customer who has a very interesting optics. So we made a model for these optics.
Mm-hmm.
And also, eventually, the mask will be part of the model, but for now, it's a file. So I'm
Yeah, yeah.
going to load the mask coming from this. If I, where is it?
So you
I
can
think,
define the mask on
yes.
screen.
Why is we define the mask?
Uh,
See, if you look at the mask, is this mask.
okay,
So it's basically a spherical mirror in that case, which is truncated on the top and on the bottom.
right.
Well, that's a specific needs for a customer, right? The mirror is pretty large. It's almost half meter in diameter. So with the mask now, we can recompute the Zernike, but also the wavefront with the mask,
Mhm,
the fringes with the mask,
mhm,
the MTF with the mask. As you can see, is not the same in X and Y
right.
because now we have a different pupil.
Mhm.
And of course, you can look at the shape of the image is the actually image you actually see from. No, this is the mask I just applied to my mirror, right? Which is not the right mirror. So it's just to show you how does it look. But that's an example of what we have already. So
Okay.
the customer actually bought the PSM. We made a custom model for his needs because by default we use circular aperture. But he had something special, so we made the mask and the model for him, and he can load it, and you can remove the mask anytime you like. Oh yeah, you can do that too, by the way. You can say, oh, my part is upside down, in fact, when I measure it. Okay, and so now you have the vertical mask. You can rotate the mask as much as you like, those kind of things. So I'm going to clear the mask, go back to circular mask. Of course, rotation doesn't matter here. That's where we are now.
Okay.
With this tool, our PSM customer can get access to all of that now. But as I just said before, this is not limited to the PSM. That's just a standard, we use the standard tool to do all of that. So if the data come from another camera, we would need some kind of interface to capture this information. Probably like here, say what the parameter of the system is. But basically, we can offer the same kind of things if there would be a value for somebody who, I don't know, who has an autocollimator and wants to do the same thing.